Part 1. The Secret. Beneath Jupiter's clouds, there's something hiding beneath the clouds of Jupiter, something we were never supposed to find. Not because it's invisible, not because it's too far away, but because it shouldn't exist at all. For decades, scientists believed they understood how giant planets like Jupiter were built. Simple, elegant models, predictable layers, logical structure. And then everything broke, because when NASA sent a spacecraft into Jupiter's orbit, it didn't just observe the planet, it uncovered a contradiction so profound that it forced us to ask a dangerous question. What if everything we thought we knew about planets is wrong? Now here's the strange part. Jupiter isn't just big. It's so massive that if it were just a little larger, it might have become a star. And yet, despite its size, despite decades of study, we had never truly seen what lies beneath its clouds, until one mission changed everything. In 2011, NASA launched a spacecraft called Juno. At first glance, it didn't seem extraordinary. It wasn't the most expensive mission, it wasn't the fastest, but it had one very specific goal: to look deeper than anything had ever looked before. Here's where things start to get interesting. Jupiter is not a friendly place. Its radiation belts are so intense that they can destroy electronics in minutes. Previous missions struggled just to survive, so sending Juno there was risky, almost reckless. But what if I told you? The real danger wasn't the radiation, it was what Juno might discover. Because scientists weren't just studying Jupiter for curiosity, they were trying to answer a much bigger question. How do planets form? And hidden inside that question is another one. How did everything begin? Now, imagine this. You're looking at Jupiter from space. You see those beautiful swirling clouds, those massive storms. It looks almost peaceful. But beneath that surface, the winds scream at hundreds of kilometers per hour. Pressure crushes everything. Temperatures rise beyond imagination, and somewhere, deep below, something is shaping the entire planet. For years, scientists had two competing ideas. The first one said Jupiter formed slowly. A solid core formed first, like a seed. Then it pulled in gas, growing larger and larger. Simple, logical, predictable. The second idea was very different. It said Jupiter never had a core at all. Instead, it formed directly from collapsing gas. No center, no structure, just chaos, organizing itself. Two theories, both widely accepted, both supported by evidence, and both completely incompatible. So which one was right? That's what Juno was sent to find out. But here's the twist. Juno didn't just travel straight to Jupiter, it actually came back to Earth first. Yes, really. After launching, it looped around the Sun, then returned to Earth, and used our planet's gravity like a slingshot, boosting its speed by over 14,000 kilometers per hour. Why go through all that trouble? Because even with advanced technology, space is still brutally expensive. Every drop of fuel matters. So Juno took the long way, a 5-year journey, nearly 3 billion kilometers, and then, in 2016, it finally arrived. Now, here's where things get weird. Juno didn't orbit Jupiter like previous missions. It took a polar orbit, flying from pole to pole, diving incredibly close, just 4,200 kilometers above the clouds. That's closer than many satellites orbit Earth. But around Jupiter, that distance is terrifying, because it meant passing through regions filled with radiation, and yet something unexpected happened. The radiation was weaker than predicted, not gone, but significantly lower, almost like Jupiter itself was hiding a safe path. And because of that, Juno survived longer than anyone expected, much longer, which meant one thing. It had time to look deeper, time to measure things no one had measured before. And what it found started with something simple: gravity. Now, gravity might sound boring, but here's the trick. Gravity tells you what's inside something without ever opening it. If a planet were perfectly uniform, its gravity would be smooth, predictable. But Jupiter's gravity wasn't smooth. It had tiny variations, subtle distortions, almost like fingerprints. And Juno could detect changes smaller than 0.01 millimeters per second. That's like noticing a change in speed, slower than a crawling insect, from millions of kilometers away. So scientists mapped Jupiter's gravity in incredible detail, and what they saw made no sense. Because the data didn't match either theory, not the solid core model, not the no-core model. Instead, it revealed something no one expected. Jupiter has a core, but not a solid one and not an empty one either. It's something in between, a fuzzy core, not a clear boundary, not a defined structure, more like a gradual blend, where heavy elements slowly dissolve into surrounding gas. Imagine dropping ink into water. At first, you see a shape, but over time, it spreads, blurs, disappears. That's what Jupiter's core looks like. And here's why that's a problem, because every model we had relied on clear boundaries, solid versus gas, core versus atmosphere. But Jupiter doesn't follow that rule, which means our understanding of planet formation might be fundamentally incomplete. And that leads to a bigger question, one we still don't have an answer to. If Jupiter formed this way, how many other planets did too? And if that's true, what does that say about our own origins? Now, before we go deeper, pause for a second. If you're enjoying this journey, if this kind of mystery pulls you in, take a moment to like the video and subscribe, because what we're uncovering here only gets stranger. Because this fuzzy core might not even be the biggest mystery. There are 3 questions we haven't answered yet, and they're all connected. First, if Jupiter's core isn't solid, what destroyed it? Second, if it formed this way, why don't our models predict it? And third, the most unsettling one, what else are we completely wrong about? We're going to answer those, but not yet, because before we can understand the core, we need to understand something even deeper, something hidden beneath pressure, beneath storms, beneath everything we can see. In the next part, we're going inside Jupiter, not just its clouds, but its structure, its energy, and the strange physics that shouldn't exist, but does. And when we get there, you might start to realize Jupiter isn't just a planet, it's a clue. Part 2, the first crack in the theory. What if the problem wasn't Jupiter? What if the problem was us? Because the moment scientists saw that fuzzy core, they didn't just discover something new, they realized something old had quietly failed. For decades, we trusted 2 elegant ideas, a solid core or no core at all. But Jupiter didn't choose either, it broke the rules. And when a planet breaks the rules, you don't just rewrite a theory, you start asking a more uncomfortable question. What else have we misunderstood? Without realizing it. Now here's where things take a strange turn, because at first, scientists thought they had a simple explanation. maybe Jupiter used to have a solid core and something destroyed it. A massive collision early in the solar system's history, violent, chaotic, a young planet smashing into another. The kind of impact that could shatter a core and mix it into the surrounding gas, creating exactly what Juno observed, a blurred, diluted interior. It sounded perfect, too perfect. So scientists did what they always do. They tested it. They built simulations, powerful models, running on supercomputers, recreating collisions between massive planets, different angles, different speeds, different sizes, again and again. And every time, the same thing happened. At first, the collision worked. The core broke apart, mixed into the planet. But then, something unexpected occurred. The material didn't stay mixed. It sank, slowly, inevitably, like sediment in water. The heavy elements separated again, reforming a clear, solid core. Over and over, no matter how they adjusted the conditions, the result was always the same. The core came back. Which meant one thing: that explanation didn't work. And just like that, the mystery got worse, because now scientists had a structure they couldn't explain, and no mechanism to create it. So they looked somewhere else, not at Jupiter, but at its neighbour, Saturn. Now, Saturn might seem like a completely different world, different rings, different appearance, different personality. But deep inside, it might be hiding the same secret. And the clue came from something unexpected. Not images, not direct measurements, but waves. He sent tiny ripples moving through Saturn's rings. At first, they looked random, beautiful, but meaningless. But then scientists noticed something. These waves weren't caused by impacts or moons. They were caused by Saturn itself. Vibrations from deep inside the planet, traveling outward, reaching the rings, and leaving patterns behind, like seismic waves on Earth, revealing what lies beneath the surface. And when researchers decoded those patterns, they found something shocking. Saturn also appears to have a fuzzy core, not solid, not empty, but layered, gradual, blended, just like Jupiter. Now, pause for a moment, because this is where everything shifts. Two giant planets, different histories, different environments, and yet the same strange internal structure. That's not coincidence, that's a pattern. And patterns means something deeper is happening, which leads to a new possibility, one that's far more unsettling than a single broken theory. What if fuzzy cores aren't accidents? What if they're normal? What if planets don't form the way we thought at all? Now imagine building a planet. In the classic model, you start with a solid core, then gas gathers around it, layer by layer, clean, structured, predictable. But what if that's wrong? What if instead everything forms together at the same time? Heavy elements and gas, mixing from the beginning, never fully separating. Creating a planet that isn't layered, but blended. Not a structure, but a gradient, like a smoothie instead of a layered cake. And if that's true, then the entire idea of how giant planets grow needs to be rethought, because suddenly, formation isn't a clean process. It's messy, chaotic, unstable, and that changes everything. Not just for Jupiter, not just for Saturn, but for every gas giant we've ever discovered, even those around distant stars. Which brings us back to one of our unanswered questions. If this is how planets form, why didn't we see it before? Why did every model, every assumption, miss this? And more importantly, what else are we missing right now? But before we go further, there's another layer to this mystery, one that's even harder to understand, because structure is only part of the story. The real puzzle is what's happening inside that structure, because deep within Jupiter, something is moving, something powerful, something we still can't fully explain. A force that creates the largest magnetic field in the solar system, a field so massive it stretches millions of kilometers into space. And yet, its origin doesn't quite make sense. Because if Jupiter's core is fuzzy, then the mechanism that generates that magnetic field shouldn't behave the way it does. But it does. Which means there's another contradiction, another piece that doesn't fit. And that leads us to the next question. What is really happening inside Jupiter that allows something impossible to exist? We're getting closer now, but not close enough. In the next part, we're going deeper, into pressure, into energy, into a state of matter so extreme it behaves like something we've never truly experienced. And when we get there, you'll start to see why Jupiter isn't just confusing, it's rewriting physics. Part 3. The engine that shouldn't work. What if the strangest part of Jupiter isn't what it's made of, but what it does? Because deep inside this planet, something is happening, constantly, silently, powerfully. Something that generates a force so vast, it could swallow entire planets. Jupiter doesn't just have a magnetic field. It creates the largest planetary magnetic field in the entire solar system, and it's not even close. If you could see it from Earth, it would appear larger than the moon in our sky. Now, think about that. A field. Invisible. Stretching millions of kilometers into space. But here's the problem. We don't fully understand how it works. And worse, based on what Juno discovered, it shouldn't work the way it does. Let me explain. On Earth, our magnetic field comes from a relatively simple process. Molten iron moves inside the core. It flows, it spins, it generates electricity. That moving electric charge creates a magnetic field. Simple, predictable. Now, Jupiter should follow the same basic idea. But instead of molten iron, it uses something far stranger. Hydrogen. Yes, the same element that makes up stars, but under Jupiter's extreme pressure. Hydrogen stops behaving like a gas. It transforms into something called liquid metallic hydrogen, a state so extreme that electrons can move freely, which means it can conduct electricity, like a metal. Now imagine an ocean of this material, deep inside Jupiter, hotter than lava, denser than anything you've ever touched, and constantly moving. That movement, combined with Jupiter's rapid rotation, creates what scientists call a dynamo, an engine, a generator of magnetic fields. And at first glance, everything seems to make sense, until you look closer. Because Juno revealed something unexpected. Jupiter's magnetic field isn't smooth, it's uneven, asymmetrical, strange, stronger in the north than the south, filled with localized hotspots, distortions, irregularities, almost like it's being generated unevenly. And that shouldn't happen. Because if the dynamo were working normally, the field would be more balanced, more uniform. But it's not. Which brings us back to the fuzzy core. Because here's where things get complicated. For a dynamo to work properly, you need motion, constant mixing, convection, hot material rising, cool material sinking, like boiling water. But Juno's data suggests something shocking. Large regions inside Jupiter may not be mixing at all. They might be stable, layered, almost frozen in place. Which creates a paradox, because without strong mixing, the dynamo shouldn't function the way it does. And yet, Jupiter's magnetic field is not just working, it's extremely powerful. So now we have another contradiction. A fuzzy core that shouldn't exist, and a magnetic engine that shouldn't behave this way. Two mysteries, connected, but not yet explained. Now here's where things get even stranger. Some scientists believe there's another layer inside Jupiter, a hidden one. A layer of helium, separating from hydrogen, slowly falling, like rain. Yes, inside Jupiter, it might literally be raining helium. Droplets forming, falling deeper through liquid metallic hydrogen, like oil moving through water. And as they fall, they release energy, heat, motion, disturbance, enough to influence the magnetic field, enough to explain why it behaves so strangely. But here's the catch. We're not sure. It's a theory, a compelling one, but not confirmed. Which means we're still guessing. And that's the unsettling part. Because even with one of the most advanced missions ever built, even with years of data, Jupiter is still holding back answers. Now let's step back for a moment. We've uncovered three major problems. First, Jupiter's core doesn't match our models. Second, its formation doesn't follow our expectations. Third, its magnetic field behaves in ways we don't fully understand. Three questions, still open, still unresolved. And remember, we're not answering them all at once, we're following them slowly, piece by piece, because the deeper we go, the stranger it gets. And we're about to go deeper still. Because Jupiter doesn't just generate invisible forces, it creates something we can see, something beautiful, something violent, something that never stops, light. In the next part, we're going to the poles of Jupiter, where the sky never goes dark, where energy from deep inside the planet collides with space itself. And what we find there might finally connect everything we've seen so far, or make the mystery even bigger. Part 4, The Lights That Never Sleep. What if the most beautiful thing on Jupiter is also the most violent? Because at the very edges of this planet, where space meets atmosphere, something extraordinary is happening. Light. Endless light. Not sunlight, not reflections, but energy itself, made visible. On Earth, we call them auroras, the northern lights, the southern lights. They appear quietly, gently shifting across the sky. But on Jupiter, there is nothing gentle about them. They don't flicker, they don't fade, they never stop. Imagine standing at Jupiter's pole, looking up. The sky is alive, rings of light, hundreds of times more powerful than anything on Earth, burning continuously. And yet, for something so visible, we still don't fully understand how they work. Now, here's the basic idea. Auroras happen when charged particles slam into a planet's atmosphere. They follow magnetic field lines, guided toward the poles. When they collide with gases, they release energy, light. On Earth, this process is driven mostly by the sun, solar wind, particles streaming through space. But Jupiter is different. Much of its aurora comes from within, not from the sun, from the planet itself, and from something else on its moons, especially one in particular, Io, a world so violent it reshapes everything around it. Io is the most volcanically active body in the solar system, hundreds of volcanoes erupting constantly, throwing material into space. Every second, tons of charged particles escape Io's surface. And those particles don't just drift away. They get captured, pulled into Jupiter's magnetic field, accelerated, and then guided straight toward the poles. Fuel for the auroras. But here's where things get strange. Scientists expected these auroras to behave in a certain way, simple currents, steady flows of energy. But when Juno measured them, the numbers didn't add up. The energy was too high, far too high. The direct currents alone couldn't explain the brightness, which meant there had to be another source, but another mechanism, and what they found was unexpected. Instead of steady flows, Jupiter's auroras seemed to be powered by alternating currents, fluctuating, chaotic, driven by turbulence in the magnetic field, especially in the north, where the field lines are tangled, complex, not smooth. And when you compare the two poles, the difference is striking. The southern aurora is structured, rounded, organized, but the northern aurora is wild, fragmented, like threads of light, breaking apart, almost as if the planet itself is struggling to contain the energy inside it. Now, here's something even more fascinating. Juno didn't just see these auroras in visible light. It looked deeper, using infrared instruments, revealing details no one had ever seen before. And in those images, scientists noticed something unusual: bright spots, trails, connections, not random, linked, each one tracing back to a different moon, Io, Europa, Ganymede, all connected to Jupiter through invisible lines of energy, like threads, binding the system together. Imagine that. Entire worlds, electrically connected, sharing energy across space. And we're only just beginning to see it. But here's the question that follows. If Jupiter's auroras are powered from within, what does that say about the planet itself? Because this isn't just surface-level activity. This is a reflection of something deeper, something happening far below the clouds, something feeding energy upward into space. And now we're starting to see a pattern: the fuzzy core, the strange magnetic field, the chaotic auroras. They're not separate mysteries. They're connected, different expressions of the same hidden system. But we still don't understand that system. Not completely. And there's another piece we haven't explored yet. Because while Jupiter's poles glow with light, its atmosphere hides something equally powerful: storms. Not like anything on Earth, not even close. Storms that have been raging for centuries, storms that reach deep into the planet. Storms that might hold clues about what's happening beneath everything we've seen so far. And one of them stands above all the others, a storm so large it could swallow Earth whole. And it's been there, watching, for over 300 years. In the next part, we're going inside that storm, and what we find there might finally start to explain what Jupiter is really hiding. Part 5. The storm that refuses to die. What if a storm could outlive civilizations? Not hours, not days, not even years, but centuries. Because on Jupiter, there is a storm that has been raging longer than modern science itself. It was already there when Galileo first looked at the sky, and it's still there today. We call it the Great Red Spot. At first glance, it looks almost familiar, a swirling vortex, bands of colour, a giant hurricane in space. But that's where the familiarity ends. Because this storm is not like anything on Earth. It's bigger than our entire planet. And more importantly, it's not supposed to last this long. On Earth, storms need fuel, warm water, energy from the sun. And when that energy runs out, the storm fades. But Jupiter is different. It generates its own energy from within. Heat rising from deep inside the planet, feeding the atmosphere above, so storms don't just form, they sustain themselves, sometimes indefinitely. Now, here's the strange part. For centuries we thought we understood the Great Red Spot, a massive, stable vortex, spinning endlessly, slowly shrinking, but still persistent. But when Juno arrived, it didn't just look at the storm, it looked inside it. And what it found changed everything. Because the Great Red Spot is not just a surface feature, it goes deep. Much deeper than expected. Scientists believed the storm extended maybe a few dozen kilometers below the clouds. But Juno's instruments revealed something surprising, at least 350 kilometers deep, and possibly more. That's not just weather, that's structure. That's something rooted inside the planet itself. Now imagine this. You're looking at the storm from above. You see the swirling clouds, the massive rotation, but beneath that, there's an invisible column, extending downward into pressure, into heat, into layers we can't directly observe. And here's where it gets even stranger. The temperature inside the storm doesn't behave the way you'd expect. Near the top, it's cooler than the surrounding atmosphere, but deeper down, it becomes warmer, almost like the storm is drawing energy from below, feeding itself, which raises a disturbing question. Is the Great Red Spot just a storm, or is it something more stable, something structural? Now let's zoom out. Because Jupiter isn't just one storm, it's covered in them, hundreds, thousands, swirling patterns across the entire planet. But at the poles, things look completely different. Instead of chaotic bands, we see organized systems. At the South Pole, 5 massive cyclones, arranged in a perfect pattern. At the North Pole, 8. Also stable, also persistent. Think about that. Storms locked in formation, not drifting, not colliding, but maintaining their positions like pieces on a board. That shouldn't happen. On Earth, storms interact, they merge, they disrupt each other. But on Jupiter, these systems seem to balance. Almost like they're being controlled by something deeper, something stabilizing them. And once again, we see the same pattern. Surface phenomena, connected to internal processes. Now remember one of our earlier questions. What is happening inside Jupiter that allows these impossible behaviors? We're starting to get closer. Because storms don't just reveal motion, they reveal structure. They show us how energy moves, how heat flows, and how stable or unstable a system really is. And Jupiter's atmosphere is telling us something very clear. This planet is not simple. It's layered, dynamic, and deeply interconnected. Now here's something even more surprising. Juno discovered storms where we didn't expect them, high in the atmosphere, at temperatures below -80 degrees Celsius, where liquid water shouldn't exist. And yet, there are flashes of lightning, storms, at altitudes once thought impossible. But these aren't normal storms. They're made of something strange, a mixture of ammonia and water, where ammonia acts like antifreeze, allowing liquid droplets to exist in extreme cold, and when these storms erupt, they don't produce rain. They produce something far more unusual: mushballs, chunks of slushy ammonia water ice, falling through the atmosphere like frozen hail from an alien sky. And as they fall, they carry material downward, mixing the atmosphere, transporting energy, changing the chemistry of the planet, and suddenly, something clicks. Because remember the ammonia distribution Juno observed? That strange, uneven pattern. This might be why. Storms, moving material in ways we didn't expect, breaking the idea of a uniform atmosphere. And once again, we see the same theme. Jupiter refuses to be simple. Every answer creates a new question. Every discovery breaks another assumption. And we're still not done. Because so far we've looked at the planet itself, its core, its magnetic field, its storms. But Jupiter is not alone. It has an entire system around it. Moons that are not just passive objects, but active participants. Worlds that interact with the planet, influence it, and may even hold secrets of their own. In the next part, we're leaving Jupiter's clouds behind and heading to one of the most fascinating moons ever discovered. A world of ice with an ocean hidden beneath its surface, and a question that changes everything. Could life exist there? Because the deeper we go, the more this story stops being about Jupiter and starts being about something much bigger. Part 6. The ocean, hidden in ice. What if one of the most promising places to find life isn't a planet at all, but a frozen moon, because orbiting Jupiter, locked in its immense gravity, there is a world that looks completely dead, a surface of ice, cracked, broken, silent. At first glance, nothing moves, nothing grows, nothing lives, but beneath that frozen shell, something may be waiting. An ocean. And not just any ocean, a global ocean, deeper than all of Earth's oceans combined, hidden under kilometers of ice. This is Europa. Now here's the strange part. Europa shouldn't have liquid water. It's too far from the sun, too cold, too exposed to radiation. Everything about it says frozen, lifeless, still. And yet, the evidence tells a different story, because scientists have seen something unusual on its surface. Cracks, long, chaotic fractures, lines that stretch for thousands of kilometers. Not random, not static, but shaped by movement. Movement from below. Imagine a frozen lake. If something pushes upward from beneath, the ice cracks, shifts, breaks apart. That's what Europa looks like, as if something inside is alive. Now, here's where Juno enters the story again. When it flew past Europa, it didn't just take pictures. It looked closer, deeper. And what it saw raised new questions. The surface wasn't just cracked, it was chaotic. Ridges, grooves, and regions that looked like they had been pushed upward from beneath. almost like something had tried to break through. But here's the real mystery. Europa's ice shell is incredibly thick, more than 10 kilometers in some places. That's not easy to penetrate. So what could possibly push through something like that? At first, scientists believed the ocean below was directly responsible. Water rising, breaking the ice. Simple, logical. But new data suggests something more complex. Instead of one vast ocean interacting directly with the surface, there may be layers, pockets of liquid, trapped within the ice itself, like underground lakes. Salty, pressurized, moving slowly, expanding, until eventually they crack the surface above them, releasing energy, reshaping the terrain. This is called cryovolcanism, ice volcanoes. But instead of lava, they erupt water, or something close to it. Now, think about that. Liquid reservoirs, inside a frozen crust, protected from radiation, shielded from space, and possibly stable, which leads to a question that changes everything. Could life exist there? Because on Earth, wherever we find liquid water, we find life, even in extreme environments, deep under ice, near volcanic vents, in complete darkness, life finds a way. And Europa has many of the same ingredients: water, energy, chemistry. But here's the catch. We haven't seen life there, not yet. We've only seen hints, clues, possibilities. And that's what makes it so compelling, because Europa sits right on the edge between what we know and what we hope. Now, remember one of our earlier questions. What else are we completely wrong about? If life exists beneath Europa's ice, then Earth is not unique, not special. Just one example of something that happens naturally. And that changes everything. But before we jump to conclusions, there's another layer to this mystery, because Europa is not alone. Another moon, even larger, holds its own secrets. And what we discovered there was just as surprising. In the next part, we're traveling to Ganymede, a world of ice and rock, with something hidden beneath its surface, something no one expected to find: an ocean. That might be even stranger than Europa's. And when we get there, we'll start to see a pattern emerging, not just on Jupiter, but across its entire system. A pattern that suggests these worlds are more connected than we ever imagined. Part 7. The moon that shouldn't have an ocean. What if the largest moon in the solar system is hiding something we almost missed? Because Ganymede doesn't look like a place that should surprise us. It's big, cold, ancient. Its surface is covered in ice and rock, craters, long streaks etched across its face. At first glance, it feels predictable. But that's the illusion. Because beneath that frozen exterior, Ganymede is hiding something extraordinary, an ocean. And not just any ocean, one that may be layered, stacked, and more complex than anything we've seen before. Now here's the first twist. Ganymede is the only moon in the solar system with its own magnetic field. Let that sink in. A moon generating a magnetic field. That means deep inside, something is moving, something conductive, something powerful, and that alone makes Ganymede unique. But it also gave scientists a clue, because magnetic fields don't just appear, they require motion, energy, structure. And when researchers studied that field more closely, they found something strange. It was interacting with Jupiter's magnetic field, creating patterns, distortions, almost like two invisible forces colliding. And from those interactions, scientists were able to infer something hidden, a conductive layer beneath the surface. And the most likely candidate? Salt water, an ocean. Now imagine that, a massive ocean trapped beneath kilometers of ice. But here's where it gets even more interesting. Unlike Europa, Ganymede's ocean might not be in direct contact with a rock. Instead, it may be sandwiched between layers of ice. Ice, water, ice, water. Like a cosmic club sandwich. Now, that might sound strange, but it actually makes sense under extreme pressure, because deep inside Ganymede, pressure increases with depth, and under certain conditions, water can freeze even when it's hot, forming exotic types of ice, denser than liquid water. So instead of a simple ocean beneath ice, you get layers, complex, stratified. And that changes everything. Because if the ocean is trapped between layers, it might not interact with the rocky core below, which means less chemistry, less energy exchange, and potentially less chance for life. But here's the catch. We're not sure. Because even with all our data, we haven't seen it directly. We're inferring, reading clues, piecing together a hidden world from subtle signals. And then Juno came along. When it flew past Ganymede, it captured images unlike anything before, close, detailed, revealing a surface full of contrasts, dark regions covered in ancient craters, light regions smoother, younger, and long streaks stretching across the moon. These streaks may be signs of tectonic activity, movement driven by heat from within, which again suggests this moon is not dead, not static, but evolving. Now here's something even more surprising. Scientists expected Ganymede's atmosphere, thin as it is, to contain oxygen, based on earlier observations, but when they looked closer, they found something else. Water vapor, far more than expected, which suggests water isn't just trapped below the surface, it's interacting with it, escaping, becoming part of the environment. And that raises a new question. If water is moving, even slightly between layers, could there be pathways for energy, for chemistry, for life? We don't know yet. But once again, we're seeing a pattern. Hidden oceans, not just on one moon, but multiple, different structures, different conditions, but the same essential ingredient, water. And that changes how we look at the solar system, because suddenly life doesn't need sunlight. It doesn't need Earth-like conditions. It just needs the right environment in the right place. And Jupiter's system might have several. Now let's step back again. We started with Jupiter. Its core, its magnetic field, its storms. Then we moved outward to Europa, to Ganymede, and now we're starting to see something bigger. This isn't just a planet, it's a system, a network, worlds interacting with each other, connected by gravity, by energy, by invisible forces, and we're only just beginning to understand it. But there's still one moon we haven't explored, and it might be the most extreme of them all, a world of fire, a place where the surface is constantly reshaped, where volcanoes erupt with unimaginable force, a world that doesn't hide its energy, it releases it violently. In the next part, we're going to Io and what we find there. It might help explain something we've been wondering all along. Where does all of Jupiter's energy really come from? Part 8. The World on Fire. What if one of the most violent places in the entire solar system isn't a planet, but a moon? Because while Europa hides its secrets beneath ice and Ganymede conceals oceans in silence, there is another world orbiting Jupiter. That does the opposite. It doesn't hide anything. It erupts constantly. This is Io. And if Jupiter is a mystery, Io is a warning, because Io is the most volcanically active world we've ever seen. Hundreds of volcanoes, some erupting simultaneously, plumes of material shooting hundreds of kilometers into space, a surface that is never still, never finished, always being reshaped. Now, here's the question, or why? Why is this one moon so unbelievably active? The answer is not inside Io alone. It's in its relationship with Jupiter and the other moons, because Io is trapped, caught in a gravitational tug-of-war. Jupiter pulls it inward. Europa and Ganymede pull it outward, back and forth, stretching it, squeezing it, over and over again. Now, imagine taking a rubber ball and constantly compressing it, then letting it expand, then compressing it again. What happens? It heats up. That's exactly what happens to Io. This process is called tidal heating, and on Io, it's extreme. The constant flexing generates enormous friction inside the moon, enough to melt rock, enough to create vast reservoirs of magma, enough to power hundreds of volcanoes. Now picture this. Beneath Io's surface, there may be a layer of molten material, not a calm ocean, but a chaotic, boiling system, pressurized, unstable, waiting for release. And when it finds a way out, it erupts. Juno captured images of these eruptions, plumes rising above the horizon, glowing heat signatures. Lava lakes stretching for hundreds of kilometers, one of them, Loki Patera, a massive volcanic depression filled with molten rock, its surface cooling, cracking, and then reheating again, like a breathing system, alive. Now, here's something even more astonishing. In 2024, Juno observed one of the most powerful volcanic events ever recorded, multiple volcanoes erupting at the same time, across a region tens of thousands of square kilometers wide, synchronized as if they were connected. And that raises a question. Are these volcanoes independent, or are they part of a deeper network, channels of magma linking them together? A system beneath the surface, far more complex than we imagined. Now, remember something from earlier. Io doesn't just erupt. It feeds Jupiter. Every eruption releases particles into space, charged particles, captured by Jupiter's magnetic field and turned into energy, fuel for the auroras, fuel for the entire system, which means Io is not just a moon. It's a contributor, a generator, part of a larger machine. And suddenly, everything connects. Jupiter's magnetic field, its auroras, its plasma environment, all influenced by this one small moon. Now step back again. We've seen ice worlds with hidden oceans. We've seen a moon made of fire. We've seen a planet with a broken core. and a magnetic field that defies expectations. This is not a simple system. It's dynamic, interconnected, and still full of unknowns. But there's one more layer we haven't explored yet, because everything we've seen so far happens relatively close to the planet. But Jupiter's influence extends far beyond that, out into space, into a vast region filled with charged particles, radiation, energy, a region so extreme it can damage spacecraft. And yet, it also holds clues about how Jupiter interacts with everything around it. In the next part, we're stepping into that invisible region. Jupiter's magnetosphere, a structure so large it stretches millions of kilometers. And what we find there might finally begin to tie everything together, or reveal that the system is even more complex than we imagined. Part 9. The Invisible Giant. What if the largest structure in the solar system is something you can't even see? Not a planet, not a star, but a field, an invisible domain, stretching far beyond Jupiter itself. This is Jupiter's magnetosphere. And it's not just big, it's enormous, so large that if it were visible in our night sky, it would appear larger than the moon. And yet, we can't see it at all, only its effects. Now imagine standing in space, far away from Jupiter. At first, everything feels empty, silent. But as you move closer, you enter something, a region filled with energy, charged particles, radiation, a space that doesn't behave like empty space, because it isn't. It's controlled, shaped by Jupiter's magnetic field. Now, here's the strange part. This magnetosphere isn't symmetrical. It's compressed on one side, stretched on the other, like a comet tail, pulled by the solar wind. On the side facing the sun, it's pushed inward, but on the far side, it extends millions of kilometers into space, a tail longer than the distance from Earth to the moon, sometimes even reaching the orbit of Saturn. Think about that. Jupiter's influence touching regions of space that far away. Now, inside this magnetosphere, something is constantly moving. A vast population of charged particles, electrons, ions, trapped, spinning, following invisible magnetic field lines. And these particles don't just come from the sun. Many of them come from Io. Remember those volcanic eruptions? They don't just release lava. They release material into space. And that material becomes plasma, charged particles, which are then captured by Jupiter's magnetic field, forming something called a plasma torus, a glowing ring of energy encircling the planet, constantly replenished, constantly evolving. Now imagine this: a moon erupts, material escapes, it becomes plasma. It feeds a giant magnetic system, which then drives auroras and shapes the entire environment around the planet, everything connected. But here's where it gets even more interesting. Juno discovered something unexpected, a second radiation belt, closer to the planet, weaker, but still present. And we don't fully understand how it formed, which means even in regions we thought we understood, there are still surprises. Now, let's talk about something else, the danger. Because this magnetosphere is not just fascinating, it's deadly. Radiation levels near Jupiter are extreme. Enough to damage electronics, enough to end missions prematurely. And yet, Juno survived. Not because the environment is safe in Te, but because there are gaps, regions where radiation is lower than expected, almost like hidden pathways, and Juno's orbit was designed to pass through them, carefully, precisely, a dance through danger. Now, remember earlier, we talked about how Jupiter's magnetic field is uneven, stronger in some regions, weaker in others. That irregularity may be shaping these radiation zones, creating pockets, safe passages, and once again, we see the same pattern. Nothing about Jupiter is uniform. Everything is complex, layered, dynamic. Now step back one more time. We've seen a fuzzy core, a strange magnetic engine, endless auroras, violent storms, hidden oceans, volcanic worlds, and now an invisible structure binding everything together. This isn't just a planet, it's a system of energy, a machine, operating on scales we're only beginning to understand. But we're not done yet, because there's one more piece of this puzzle. Something subtle, something easy to overlook, but incredibly important: time. Because Jupiter is not static, it's changing. Slowly, quietly, in ways we're only just starting to detect. And those changes might reveal something even deeper. In the next part, we're going to look at how Jupiter evolves, how its magnetic field shifts, how its internal processes change over time, and what that tells us about the future of this giant planet. Because the story of Jupiter isn't just about what it is, it's about what it's becoming. Part 10, a planet that changes. And if Jupiter is not the same planet today as it was yesterday, not in obvious ways, not in ways we can easily see, but slowly, quietly, changing. Because for a long time we thought of giant planets as stable, timeless, unchanging, massive systems that evolve so slowly. They might as well be permanent. But Juno revealed something different, something subtle but deeply important. Jupiter is evolving. And one of the clearest signs comes from its magnetic field. Now, on Earth, our magnetic field changes over time. It drifts, weakens, strengthens, even flips. This process is called secular variation. And it happens because of changes deep inside the planet, movements in the core, flows of molten material. But Jupiter was expected to be more stable, too large, too powerful. Its internal processes should smooth things out. But that's not what Juno found. Instead, scientists detected changes, slow shifts in the magnetic field, especially in one region, a region now known as the Great Blue Spot, a concentrated patch of intense magnetism, unlike anything we've seen on Earth. And over time, this region is moving, changing shape, evolving. Now think about what that means. The magnetic field is not fixed. It's alive, responding to processes deep inside Jupiter, processes we don't fully understand. Now here's where things connect again, because remember the fuzzy core, that blurred, mixed region deep inside the planet? It may play a role here. Because if Jupiter's interior is not cleanly layered, but gradually mixed, then the flow of material inside it will be complex, uneven, and that could explain why the magnetic field is uneven too, why it shifts, why it evolves. Now add another piece: rotation. Jupiter spins incredibly fast, one full rotation in just about 10 hours. That rapid spin stirs everything inside, driving motion, creating currents, feeding the dynamo. But it also introduces instability, because different layers may rotate at different speeds, sliding past each other, creating shear, and that shear can change how energy moves, how magnetic fields form, how the entire system behaves. Now here's something subtle, but fascinating. We don't actually measure Jupiter's rotation by watching its clouds, because the clouds move. Different bands travel at different speeds. Instead, we measure it through the magnetic field, because that field is tied to the deep interior, to the true rotation of the planet, which means every change in the magnetic field is a clue, a signal, a glimpse into something we cannot see. Now step back again till we've followed a chain of discoveries from the surface to the core, from storms to magnetic fields, from moons to invisible structures, and now to time itself. And what we're seeing is not a static object, but a system in motion, evolving. And that leads us to one final question. Not about what Jupiter is, but about what it means. Because if everything we've seen is true, then Jupiter is not just an isolated case, it's a model, a clue, a window into something much larger. In the next part, we're going to zoom out, beyond Jupiter, beyond our solar system, and ask a question that changes everything. What does Jupiter tell us about planets across the universe? Because once you understand Jupiter, you start to see it everywhere. Part 11. The pattern beyond Jupiter. What if Jupiter isn't special at all? Well, not unique, not rare, but common, because once we began discovering planets beyond our solar system, something unexpected happened. We started finding worlds that look a lot like Jupiter, but bigger, hotter, stranger, gas giants orbiting distant stars. Some so close to their stars, they complete an orbit in just days. Others, farther out, colder, more familiar. But here's the key detail. Many of them don't match our original models either, just like Jupiter. Now think about that. For years, we built theories based on a handful of planets: Mercury, Venus, Earth, Mars, Jupiter. We assumed those patterns were universal. But when we looked outward, the universe didn't follow our expectations. It surprised us, again and again. And Jupiter was the first warning. Because now, with Juno's discoveries, we're starting to realize something deeper. If Jupiter's core is fuzzy, if its structure is mixed, if its magnetic field is uneven, then perhaps these are not exceptions, they're the rule. Now, imagine a distant star system. A young star, surrounded by a disk of gas and dust. Planets begin to form, but instead of neat, layered structures, they emerge as chaotic blends, gas and heavy elements mixing together, never fully separating, creating worlds with fuzzy interiors, dynamic structures, complex magnetic fields. Now, suddenly, many of the strange exoplanets we've observed start to make more sense. Hot Jupiters, inflated atmospheres, unexpected densities, all of them may be part of the same pattern. A pattern we didn't recognize until we understood Jupiter better. And that leads to something even more profound, because Jupiter didn't just form in isolation. It shaped our solar system, its gravity, influenced everything. Asteroids, comets, even Earth. Some scientists believe Jupiter may have played a role in delivering water to Earth, deflecting icy bodies inward, or preventing others from reaching us, acting as both a shield and a gatekeeper. Now imagine removing Jupiter from the equation. Would Earth still exist? Would life have had the same chance to develop? We don't know. But the possibility is unsettling, because it suggests our existence may be tied to a planet we barely understand. Now, take that idea and extend it outward. If Jupiter-like planets are common, then systems like ours may also be common. And if that's true, then the conditions for life might not be rare, but they might be everywhere. But here's where we need to be careful, because understanding Jupiter doesn't give us all the answers. It gives us better questions, and we still have several left unanswered. Remember them? What destroyed or created the fuzzy core? Why do our models fail to predict it? And how does Jupiter's internal engine really work? We've made progress, but we're not done. And that's what makes this story so compelling, because every discovery opens another door, and behind each door is something we didn't expect. Now, there's one more step, one final perspective, because we've looked at Jupiter as a planet, as a system, as a model. But what if we look at it as something else, a message? In the next part, we're going to step back one last time and ask, what is Jupiter trying to tell us? Not just about planets, but about how science works, how knowledge evolves, and why the universe keeps surprising us. Part 12. The message hidden in the storm. What if Jupiter isn't just something we study, but something that teaches us? Because beneath all the data, all the measurements, all the discoveries, there's a pattern, not just in the planet, but in the way we understand it. At first, we thought we knew Jupiter. A gas giant, layered, predictable, a planet that followed rules. But then Juno arrived, and quietly, without drama, without announcement, it showed us something simple. We were wrong. Not completely wrong, but incomplete. And that distinction matters, because science doesn't fail when it's wrong. It evolves, it adapts, it corrects itself. And Jupiter is a perfect example of that process. We built models, we tested them, we trusted them, and then we found something they couldn't explain. A fuzzy core, a magnetic field that shouldn't behave the way it does, auroras powered from within, storms that last for centuries, moons that shouldn't have oceans, but do. And instead of ignoring those contradictions, we followed them. That's the real story. Not just what Jupiter is, but how we respond when reality doesn't match expectation. Now, here's something subtle, but powerful. Every time we discover something unexpected, we're faced with a choice: ignore it or explore it. And exploration is what moves us forward, because the universe doesn't adjust to fit our ideas. We adjust to understand it. Now think about the three questions we've been carrying. What created Jupiter's fuzzy core? Why don't our models predict it? And how does its internal engine really work? We've come a long way. We've seen possible answers, collisions, layered formation, helium rain, but none of them fully solve the puzzle. And that's okay, because not knowing is part of the process. It means we're close to something new. Now, let's zoom out one last time. Jupiter is not alone. It's one planet, in one system, around one star, in a galaxy of billions, and yet, studying it has already changed how we think about all of them, about how planets form, how they evolve, how they interact, and maybe how life begins. Because hidden in this giant world are clues. Clues about structure, energy, complexity, clues that extend far beyond Jupiter itself. And that's what makes this story so powerful. It starts with a planet, but it leads to everything. Now, imagine the future. New missions, better instruments, returning to Jupiter, diving deeper, exploring its moons, landing on Europa, drilling through ice, searching for life. Each step bringing us closer, not just to answers, but to better questions. And that brings us to something important, because if you've followed this journey from the clouds of Jupiter to its hidden core, to the oceans of its moons, then you've already experienced something rare. The moment when understanding begins to shift, when the familiar becomes unfamiliar, when curiosity takes over, and if that feeling stayed with you, even for a moment, then you're already part of the process. So, before we go further, take a second. If this journey made you think, if it made you wonder, let me know. Leave a comment, share your thoughts. Because the best questions often come from unexpected places, and they're the ones worth following. Now, there's just one final piece left, one final perspective. Because everything we've seen so far leads to a deeper realization, not about Jupiter, but about us. In the next part, we're going to bring it all together and answer the question that's been quietly building the entire time. Why does this matter? Part 13. Why this matters. What if this entire story was never really about Jupiter? Not just a planet, not just a mission, but something deeper. Because when you strip away the clouds and the storms, the data, what you're left with is a realization. We are still at the beginning. Even now, even with everything we've discovered, we are only just starting to understand the universe we live in, and Jupiter is proof of that. Think about it. For centuries, we looked at Jupiter through telescopes. We saw its bands, its storms. We thought we understood it. Then we sent spacecraft. And everything changed, because the closer we looked, the more complicated it became. And that's not a failure. That's progress. Now, here's why this matters. Because Jupiter is not just a distant world. It's part of the system that made us possible. Its gravity shaped the solar system. Redirected asteroids, stabilized orbits, possibly even influenced the conditions that allowed life to emerge on Earth. Which means, in a very real way, Jupiter is part of our story. Now extend that idea. If planets like Jupiter are common, then systems like ours may also be common. And if that's true, then the ingredients for life may not be rare. They may be everywhere. But here's the deeper point. Understanding Jupiter is not just about finding answers. It's about learning how to ask better questions. Because every discovery we've made has followed the same pattern. We observe something, we build a model, then reality challenges it, and we adapt. That cycle is how knowledge grows. Now, think about the questions we started with. What lies beneath Jupiter's clouds? How did it form? How does it work? We don't have complete answers, but we have something just as valuable: direction. We know where to look. We know what doesn't work. And we know that the truth is more complex than we imagined. And that changes how we approach everything, not just planets, but science itself, because it reminds us of something important. Certainty is temporary. Understanding is always evolving. And the universe is under no obligation to be simple. Now, here's something worth holding on to. Every time we discover something unexpected, we expand the boundaries of what's possible. A fuzzy core, an ocean beneath ice, volcanoes on a moon, each one, once unimaginable, now part of our understanding. And there are more waiting. Far more. Because Jupiter is just one world, one example among billions. And if one planet can challenge everything we thought we knew, imagine what the rest of the universe is hiding. Now, take a moment. Think about where we started. A question. What lies beneath Jupiter's cloud, and where that question led us? To new models, new mysteries, new possibilities. And that's the real answer. Not a single discovery, but a process, a journey, one that doesn't end. Because every answer leads to another question, and every question takes us a little further. Now, there's one final step, one last piece to bring everything together. In the next part, we're closing the loop, returning to the beginning, and seeing Jupiter, not as a mystery anymore, but as something else. A key. Part 14. The key we didn't know. We had what if Jupiter was never the mystery? What if it was the answer? We didn't know how to read, because from the very beginning, we were asking the wrong question. We asked, what is Jupiter made of? What lies beneath its clouds? How does it work? And those questions led us far, but they also limited us. Because Jupiter isn't just an object to analyze, it's key. It's a system to interpret, a pattern to recognize, a key. Now think back to everything we've seen. A core that isn't solid, a structure that isn't layered, a magnetic field that isn't uniform, storms that don't fade, moons that aren't passive, an environment that isn't isolated. Nothing about Jupiter fits neatly into our categories, and that's the point, because nature rarely follows clean definitions. It blends, it overlaps, it evolves. And Jupiter is one of the clearest examples of that. Now, here's the shift. Instead of asking, what is Jupiter? Ask this, what does Jupiter represent? Because once you do that, everything changes. Jupiter becomes a model of complexity, a reminder that systems are interconnected, that surface features are linked to deep processes, that nothing exists in isolation. Its storms are tied to its internal heat, its magnetic field is tied to its structure, its auroras are tied to its moons, its evolution is tied to time. Everything connected. And once you see that, you start to recognize it elsewhere, on Earth, in ecosystems, in climate systems, in the way energy flows through environments. The same principles, different scales. Now zoom out even further to other planets, other systems, on other stars, and suddenly Jupiter isn't just one example. It's a pattern, a blueprint of how complexity emerges, not from simplicity, but from interaction. Now here's something subtle but powerful. For a long time, we searched for simple answers, clean models, clear boundaries. But Jupiter shows us that reality is often something else, messy, blended, dynamic, and that doesn't make it harder to understand. It makes it richer, because complexity carries more information, more clues, more opportunities to learn. Now, think about the three questions we've carried from the start. What created the fuzzy core? Why don't our models predict it? How does Jupiter's engine really work? We still don't have final answers, but now we understand why. Because we were trying to fit a complex system into simple frameworks, and Jupiter refused. So instead, we adapt. We build better models. We embrace uncertainty. We follow the data. And step by step, we get closer, not to perfect answers, but to deeper understanding. Now, here's the final realization. Jupiter didn't just change what we know, it changed how we think. And that might be its greatest contribution also. Because once you start seeing the universe this way, you stop expecting simplicity, and you start looking for connections, patterns, relationships, and that's where real discovery happens. But we're not done yet. There's one final piece, because a key is only useful if you know what it unlocks. In the final part, we're going to open that door and see where it leads. Part 15, the door. It opens. What if everything we've learned about Jupiter is pointing somewhere else? Because a key only matters if it unlocks something. And Jupiter has been quietly unlocking doors this entire time, not just about itself, but about everything beyond it. Now imagine this. A distant star system, a young star surrounded by a swirling disk of gas and dust. Planets begin to form, some small, rocky, others massive, gas giants, and for a long time we assumed we understood how this process worked. But Jupiter changed that. Because if planets can form with fuzzy cores, if their interiors are mixed, if their magnetic fields are complex and uneven, then planet formation is not a clean process. It's chaotic, dynamic, and far more flexible than we imagined. Now apply that idea to the thousands of exoplanets we've discovered, worlds that don't fit our expectations, planets too large, too hot, too close to their stars, planets with densities that don't make sense, atmospheres that shouldn't exist. For years, these worlds felt like exceptions. But now, they may be something else. They may be normal. And Jupiter was the first clue. Now, here's where things get even more interesting. Because gas giants don't just form systems, they shape them. Their gravity influences everything around them. They can scatter smaller planets, redirect comets, stabilize or destabilize entire regions. Now, think about our own solar system. Jupiter sits in a very specific place, far enough from the Sun to remain stable, massive enough to dominate its region, and its presence may have protected Earth, or at least helped create the conditions where life could emerge. Now, imagine a system without a Jupiter. More impacts, more instability, a very different history, and possibly no life. Which means understanding Jupiter is not just about curiosity. It's about context. It tells us what kind of systems can support life, what conditions matter, what patterns to look for. Now, take that one step further. If we find another star system with a Jupiter-like planet in a similar position. Well, what does that suggest? It suggests possibility, maybe even probability, and suddenly the search for life becomes more focused, more informed. Now, here's the deeper layer, because Jupiter doesn't just influence planets. It influences ideas. It forces us to rethink assumptions, to question models, to explore new possibilities, and that mindset is what drives discovery. Now, remember where we started. A simple question. What lies beneath Jupiter's clouds, and where it led us? To fuzzy cores, to magnetic mysteries, to hidden oceans, to volcanic worlds, to interconnected systems, and finally, to a broader understanding of the universe. That's what Jupiter unlocks. Not just answers, but perspective. Now, there's one last step, because every journey needs a return, a moment to look back, to see the path clearly, and to understand what it all means. In the final part, we're going to close the loop, bring everything together, and answer the question that's been quietly building from the beginning. What did Juno really discover? Part 16. What Juno really discovered. What did Juno really discover? Not just data, not just images, not just a deeper look at Jupiter. It discovered a shift. A shift in how we see one planet. And more importantly, a shift in how we understand all planets. Because when Juno arrived at Jupiter, we were expecting answers. Clear ones. A solid core, or no core, a predictable structure, a system we could neatly describe. But instead, we found something else, a planet that refuses simplicity, a fuzzy core, a magnetic field that doesn't behave, storms that last centuries, auroras powered from within, moons that interact, influence, and evolve. And an invisible system, binding it all together. Juno didn't just reveal what Jupiter is, it revealed what our models were missing, and that changes everything. Because science isn't about being right, it's about getting closer, closer to reality, closer to truth. And sometimes, getting closer means letting go of what we thought we knew. Now, look at Jupiter again, not as a distant gas giant, but as something else, a system of interactions, our energy moving through layers, forces shaping structure, time changing everything. And suddenly, it doesn't feel distant anymore, it feels familiar. Because the same principles exist everywhere, on Earth, in ecosystems, in weather, in the flow of energy through living systems, different scale, same patterns. And that's the deeper discovery, not just about Jupiter, but about the universe itself. It's not built from isolated pieces. It's built from connections. Now, think about the three questions we carried from the beginning. What created the fuzzy core? Why don't our models predict it? How does Jupiter's engine really work? We still don't have complete answers. But now, we understand something more important. Why those questions exist. Because the universe is more complex than our first explanations. And that complexity is where discovery lives. Now imagine the future. New missions returning to Jupiter, landing on Europa, exploring oceans beneath ice, studying Io's volcanic systems in detail, mapping the magnetosphere with even greater precision. Each mission adding another piece, another layer, another step closer. And maybe one day we'll answer those questions completely, or maybe we'll discover something even more surprising. Because that's the pattern. Every answer opens another door. And that's the real discovery, not a final conclusion, but a continuous journey. Now, before we end, pause for a moment. If this journey changed the way you see the universe, even slightly, then stay curious. Because curiosity is what drives everything forward. And if you want to keep exploring mysteries like this, take a moment to like the video. Subscribe to the channel and share it with someone who loves questions without easy answers, because the next mystery is already waiting. And it might be even stranger than this one, but it starts the same way, with a question.